In this video, we're going to learn how we can understand the query plan that's outputted from the explain statement. And in the second part of this video, which you'll find a link for here, we'll actually look at the explain analyze statement. But let's start with the basics. Now we're going to be doing this using a Postgres database. So if you're using another type of relational database system, then there may be slight differences here because we'll be focusing on kind of the Postgres version, but generally these principles should hold true. If you're using a data warehouse, you need to be a little bit more careful because generally the way that you're going to analyze performance in a data warehouse is going to differ compared to what we do in Postgres, for example. And you may actually have your own analytical tools there, which will show you and help you dive deeper into how your query is executed and also where the biggest cost components are. But first things first, we actually need to create our own table. So we're going to use this syntax here to just create a basic table for us. We're going to have references to a user ID as well as an event ID, but we're actually not going to create these tables just kind of for simplicity. And we're also going to insert just 2 rows of data so that we actually have some sort of data to query. All right, so let's start off with a very simple query. First, we're going to do a select statement here with a where clause, and then we're just going to put the explain keyword beforehand, which is going to actually produce the query plan for us without executing the query. And then here we can see the output of that result. So let's take this step by step. The first thing that we need to know is that this explain keyword is actually going to generate the query plan for us. In essence, it means this is what the database query planner decided was the most optimal way to fetch the results for us, to produce that final result set. Obviously, our query is relatively simple here, so there's not a lot of steps that need to be taken, but as our queries get bigger and more complex, these plans can obviously get a lot longer since a lot more steps need to be taken to reach this final result. In our case here, we can just see a single node outputted. We start off with a Secscan, which stands for a sequential scan, which essentially means we're going to be looking through all of the data in our table. Now, when you think about that, that's probably not very ideal, right? If your table is extremely large, then going through all the data in your table just to find the relevant rows is going to be problematic. Obviously, in our case right now, it's not a big issue because we only have 2 rows of data. But if you think about extending this to tens of millions of rows, then this is something that you're going to want to be aware of. And we can see below there, we also have a filter clause. And this is where our where condition currently lies. So essentially what this node is doing for us is it's going through all the data in our table with this sequential scan, and then it's applying that filter condition that we can see here to filter out all the non-relevant rows and really only keep the information that it needs. Now, next to the sequential plan, we actually also see some additional interesting metrics. And the first things that we see is this 0.00 and then a couple of dots and then 21.50. And this tells us about the estimated cost of this query. And so the first component here is the setup cost. So anything before the first row of data is going to be returned by this query. And then what we have afterwards, this 21.50, is going to be the total cost of the query. In our case, we can see that there isn't really any setup cost associated with it. And then the total cost of the query from start to all the way until the last row is returned is this 21.50. Now, in the explain part, these are essentially arbitrary units and you don't really have to think about any certain meaning to them. They become extremely useful when we have multiple nodes, which is also what we'll see in a little bit when we look at a little bit more of a complex query so that you can actually compare the cost of different components. The other things that we have are also this rows as well as also the width. The rows tell us about the estimated number of rows returned by this query. So right now our query planner estimates that 5 rows are going to be returned. Obviously, we know it's not possible because you only have 2 rows in our table, but you know what, close enough for now. And then the width tells us about the estimated size in bytes of each row that we have. So in this case, we're going to estimate about 60 bytes per row. And so these are the different components that make up our individual node. And we'll see even when we get to more complex queries, this information is essentially going to be repeated for us. So now that we have this very basic query plan, let's try to optimize this a little bit. What we can see again from our query plan is that we have this sequential scan. So essentially scanning through the whole table. Well, a common way that we can go about optimizing this is instead using an index. And what an index essentially does is it's going to create a lookup table for us where we know exactly what rows fit certain filter conditions based on what we created the index on. So, for example, if we're filtering here by user ID, if we create an index on this user ID column, then we're going to keep a mapping of the different values that we can find in this user ID and also what rows contain these values. And so in that way, if we're doing a very specific filter like we do in this case, we actually can directly find the subset of rows that need to be retrieved. However, if we run this in our current case, our query plan is actually going to look exactly the same. Now you might be wondering, well, why is that the case? We added an index, why aren't we using the index? Now the index only really comes into use when we're querying about less than 5 to 10% of our data, and otherwise our query planner may actually decide that it's more optimal to just directly do the full table scan. Now the reason for this is that the index lookup actually requires an extra I/O operation, and this reading from disk and these input-output operations are actually the most expensive part of all of these database queries. So retrieving that data and getting all of that is the most expensive component. And so the more that we can minimize the amount of data that we have to read, the faster our queries are going to be. And so at some point, it actually becomes more optimal to just go through the whole table versus first looking up the index and then retrieving all of those small relevant bits of information that may be scattered all over the place. Instead, we can just kind of scan through our data in a much more efficient way, and that will actually end up being faster for us. However, if we use this Python script here to just insert a bunch more rows and then re-execute the same explain statement, we can see now that the result data set that we're having is smaller than the total amount of data that we have in the table. And so at this point, we're actually going to properly be using our index, because at this point it actually becomes more efficient to do this index lookup than it would be to scan through all the data in our table. Now obviously this is just a toy example, and you may also be wondering, well, if we have this 5 to 10% threshold, why did we need to add an extra about 220 rows? Why couldn't we just add an extra 10? Well, because we have an extremely small table, there's actually another component that factors into this, which is called the buffers. Because when we're reading data from disk, we're not actually reading an individual row, but we're reading a block from the disk, which includes a whole set of information. And so if we're retrieving these blocks, which usually contain at least several rows, then really we're never reading an individual row, but we're reading chunks at a time, because that's kind of the minimum size at which we can actually read data from disk. And so even if we had 10 rows in here, because we would be reading chunks at a time, because that's the minimum amount that we can read at once, it again wouldn't make sense to use the index, because a full table scan would essentially still only be reading one block. And so because we're dealing with these very small tables, we really only get the use of the index when we have enough data to, of course, go across this percentage threshold, but actually have enough data to spread it out over several different blocks on disk so that it becomes more efficient to read the index and then go and find the relevant block that our data is contained in, versus just reading the block directly and having less I/O operations on that side. And so we can also see, just kind of coming back to this new query plan, we're no longer doing our sequential scan like we did previously, but instead we're doing an index scan, where we're using our index to actually find the relevant values. And we can actually also modify this by searching for several values within this index, and our index scan here is just going to be updated, and we're going to look for several different index conditions, which works because we have all these values indexed, and so we know exactly what we're looking for. However, if we add a second component to our filter clause here, then we're actually going to be looking at a slightly different thing. We can still use our index scan to find the relevant rows, but because we don't have an index on this joint filter condition here, we still have to do some sort of extra filtering, which is this extra filter row that we see. So we still do an index scan and we find the relevant rows that we need based on our index condition, but because we have an extra component in our filter, we actually need to apply this extra filter clause on the rows that we've received to make sure that our whole where clause here is properly abided by. We could obviously fix this if we wanted to by adding now another index on these two columns together, but we always want to be careful about that, because adding more indices is actually also going to just cause general more load on our database, because every time data is inserted, updated, deleted, our indices need to be updated. They need to be maintained and kept up to date. And so the more data we have and the more indices we have, the more this is actually using up resources in the background. And so we want to be careful that we don't actually add unnecessary indices, because in this case, we're already reading a very small amount of data because we're just doing a direct where clause, and we're just filtering out for a specific condition to be met where we know that this result is going to be small. And so actually just applying that filter on the resulting rows is going to be pretty efficient for us versus having to create another index for this. Obviously, if the resulting data set is going to be massive, and having a second index can greatly reduce the amount of data that we actually need to fetch from this is going to be a benefit to our performance. However, if the final result is barely going to change and you're already reading in a very small amount of data from your first index filter component, then adding this extra index versus just doing the filter after doing the index lookup isn't really going to benefit your performance. In fact, like I mentioned earlier, it may actually harm it in the long run because you can have a lot of indices that you're not using or that are not really necessary that constantly need to be maintained as data is updating and changing in your database. All right, so let's go past this very basic example and look at a little bit more of a bit more complex query. By the way, if you're watching this and you're still just getting started with learning programming and SQL and all this good stuff, but you want to become a software engineer, make sure to check out my Udemy course. It's a 40+ hour course where you'll learn all the basics, starting from absolute zero programming knowledge to learning Python, building an application, learning SQL, integrating databases, caching, linting, using GitHub Actions, creating a CI/CD flow, all that good stuff so that you can actually have this technical foundation to start getting into software. But let's get back to it. So we're going to add a second table, which is going to be an event table, and this is just going to hold the mapping of event ID to some sort of name. And we're going to insert some values into it just so that we can do an actual join. And then if we run an explain on this join statement where we select from our user event log and join on this new event table that we created and look at the query planner output, we can see that it's actually a little bit more complicated. The first thing that we'll notice is we actually have a series of indentations, and we have essentially here a series of different nodes, of different steps that need to be taken. And the way that we read this more complex query plan is we start with the innermost indentations and then we just work our way outwards. So if we start from the very inner component, which is our sequential scan of the events table, we can see here we're reading the whole events table through our sequential scan, and then we're applying the filter condition. The next thing that we're doing is we're loading the results into a hash table, an in-memory hash table, which is going to be a lookup map for each of these values to the corresponding value. And then on the same row, what we have is also a sequential scan on our user event log table. And so now we have two nodes on the same level. And the first node is going to be our outer child, and the second node in the bottom is going to be our inner child. And so what happens is for every row produced by our outer child, we're going to look for a matching row in our inner child using the join condition that is provided above. And so this is how we go about the joins here, that we're creating this in-memory hash table, and we're creating a hash table because the data that we actually have is small. And then for every row that we're getting for our bigger select here, we are then joining using our join condition as well as the in-memory hash table that we've created previously. And all of this together then is going to give us our final results. And we can see here each component still has the same kind of informational breakdown that we've seen previously. However, what is important to know is that these cost components are actually cumulative. So as we go up in our operations and as we kind of go from our beginning to our end results, our startup costs as well as our total costs are actually going to include also the cost of all of the child components. So you can see our costs are getting bigger and bigger because these cost components are cumulative. Now, depending on the size of your table, you probably won't always see a hash join here, and you can also see other types of joins, but the principle here is going to be the same, that we have two resulting rows, and for our outer child, we're then going to use the results of the inner child to fulfill this join condition. Now the join strategy again may differ based on how much data we're actually getting. You can't always store everything in memory, so sometimes you have to take a different approach, but the way that we're going to be reading these things is going to be the same. Now obviously SQL is more than just a select, a where, and a join clause. However, the principles that we've learned here and the way of understanding the different components of this explain statement are going to transfer to all the other keywords that you're actually going to be using. So you can use the same approach and the same way of reading it to, look at your more complex queries to understand what are the biggest cost factors and what are the things that I should be considering here. So, in summary, just think about the explain statement gives us the plan that our query optimizer thinks is the best way to get this data. And we have estimated cost components for each step where it thinks, okay, this is about how expensive these operations are going to be. Now, the biggest important factor to determining the fastest query is essentially how much data do we actually need to shuffle around, do we need to get from disk and to deal with. And so if you're thinking about optimizing your queries, always think about how can I reduce the actual amount of data that I have to deal with. Now in part 2 of this video series, we're going to be looking at the explain analyze statement, where we actually also run the query rather than just looking at the query plan, and we get some extra informational statistics there. So make sure to also check out part 2 to understand how we can use this extra information to help us even more in understanding our query performance and the query plan and how these two may actually differ.